All right. So kind of get started here. Kind of mentioned a couple things off the top that are maybe a little bit concerning to me. Um, so one, trying to reiterate this, but like you're having issues with Stata. Now is not the time to still trying to be resolving them, right? The assignment is due tomorrow at the end of the day. So I tried to stress to kind of come into my office like earlier last week, this week. I think for everyone who has, I think you can agree, like we've been able to resolve a lot of the issues or concerns you're having, kind of get you on the right path. So that assignment is due tomorrow. When you upload your answers, you need not only your answer to the question, but any code that got you to that point. So when you're uploading your do file, it needs to include both the code that you've used, also your answer to the question, right? As we kind of work through examples today, I'll kind of mention what this looks like and how you need to have both components, okay? So after class today, we'll have covered the material that is also sufficient to answer all the questions in where quiz number 1. So I've got those practice problems. A lot of it was material that we covered last week or the week before. So it's everything kind of up to this point. The practice problems give you a really good idea about what those quiz questions will look like. That'll be kind of open, set to be due at the end of the day Monday as well. So hopefully you've been preparing to kind of take that quiz. It'll be open until the end of the day Monday. All right. So in addition to that, what we will do today is finish up the material required for that quiz. We've already covered everything that would be required for that problem set. So this is where starting reviewing for those quizzes and starting those problem sets early will be beneficial. So even after today, I'll post up the next problem set either later today or early tomorrow morning. You can kind of start working on the first few questions based off of what we get through today. Right? And then as we kind of progress through things, you can answer more and more of those. So, excuse me. Where did we leave off? Yeah.
Just want to clarify once again the quiz that's ECON that's like once you open just 1 hour, right?
Yeah. So once you open it, once you start it, you can't pause, right? You need to be prepared to kind of take it and finish it in that next 60 minutes. Yep. So that means you need to start it before when? If you want the full hour, you need to start it before 10:59 tomorrow, right? Or not tomorrow, on Monday. Yep. So we left off kind of thinking about, we can look at do hypothesis testing for sample means. We can also do hypothesis testing for different statistics. Right? So one that we talked about was kind of thinking about this correlation coefficient. Right? Maybe we want to do some hypothesis testing for this. I think up to last class, we stopped at this difference in means. So we said, in general, the structure that we have for calculating this test statistic is take whatever statistic we're interested in. Here is the difference in means as opposed to just one mean. We'll subtract the assumed true difference and then divide by the standard deviation of whatever statistic we're looking at. So we only had one population. Let's see if I can get it up here. Somewhere back in here. Well, let's go back. Right, we had one population. The statistic we were looking at was just the mean, and the denominator represented just the standard deviation of that one mean. So we could do the same thing, but for differences in sample means. Okay. So we did a lot of this hypothesis testing stuff. The next thing that we're going to do is kind of draw this connection between hypothesis testing and what we call confidence intervals. Okay. So I think to set this up, I'll start out thinking about how we could make what we call type 1 and type 2 errors. So we'll kind of go here. We work through the p-value approach. How are we going to make type 1 and type 2 errors? Okay. So we had this null hypothesis. We then used our sample data to see if we could reject or fail to reject that assumption. Now, sometimes we'll be rejecting the null when in fact we shouldn't be, right? So if I think about this setup that we had, we said if we take a sample size over 30, let's assume we were doing kind of this two-tailed test, and we assume that the true mean for this variable was 105. Our sample means should be normally distributed around that value. Now, if we set up a kind of two-tailed test, and let's say we wanted to compare it at the, and here we've got different confidence levels. So we said the alphas that we were using were 0.1, 0.05, 0.01. We'll start using this terminology of significance and confidence levels. So this is the 10%, 5%, 1% significance levels, which correspond to 90, 95, and 99% confidence levels. I think we'll see this once we talk about confidence intervals today. Okay? Now, sometimes what we could see happen is, and here we'll assume we don't have the known population variance, so when we calculate this test statistic, it won't come from the standard normal, it'll come from the student t distribution. Well, let's assume that what we assume to be true is in fact true. There are still going to be instances where I see a sample mean that is high enough that, remember, kind of that desired alpha in the tail. So here we could use 0.05 in both tails, which means my total alpha is 0.1. The critical values that gave that to me were positive and negative 1.65. Even if what I assume to be true is true, 10% of the time, I'm still going to see sample means that result in the test statistic where that test statistic absolute value is greater than the absolute value of my critical. So I'm going to reject even though I shouldn't be, right? What I assume to be true, if it is in fact true, for every sample mean, if I took 1,000 different sample means, I kind of went through this exercise, I think a little bit already, but for some of this, for 10% of the time, even if what I assume to be true is true, I'm going to be making errors 10% of the time. I'll be seeing sample means out here where I'll reject even though what I assume to be true is in fact true. We'll call this our type 1 error. Okay? So type 1 error, we're essentially setting it. Because when I set alpha, that's the, in decimal form, percent of the times I would be making this type 1 error. Now, type 2 error is a little bit more difficult, but essentially the type 2 error is if I have this assumed true mean, let's say I see a sample mean that's right here. That's going to result in a test statistic where I will do what? Reject or fail to reject the null. Is that test statistic greater than my critical value and absolute value? It's to the left. That means it is smaller, right? So I would fail to reject. However, what if my assumption was in fact not true and the true mean was way down here? Well, then we'd be making what we call a type 2 error. I failed to reject this assumption, even though in fact the true mean was something like 100. Right? So when I fail to reject, even though I should have been rejecting, we call that a type 2 error. Okay? So we're going to be making these type 1 and type 2 errors, right? We can't really prevent ourselves from making them. So you can kind of think about these different combinations. If I reject the null, when in fact it was false, I'm making the right decision. If I failed to reject it when it was true, well, that was the right decision as well. This different combination, when I rejected, even though I shouldn't have been, that's my type 1 error. When I failed to reject, even though I should have been, that would be my type 2 error. Okay. So we're then going to relate this, right? So I always kind of use this example, right? An obvious kind of type 1 error is I, reject the null. I assume the person's not pregnant. I reject that. Well, clearly I'm wrong, right? Whereas here I'm failing to reject that they're not pregnant. Well, clearly I should be rejecting, right? This is my type 1, type 2 error. Okay. So I mentioned this already. We're setting that type 1 error. We won't dive into the type 2 error exactly where that comes from, but it is going to be somewhat correlated or related to this type 1 error we're setting, right? So we won't dive deep into this, but our type 2 error will be related to the type 1 error, but we won't kind of dive into that relationship in this class, right? So what we're really going to focus on is we're setting alpha. We're setting that significance or confidence level. We know that we're setting ourselves up to make a certain percentage of type 1 errors. And we're okay with that, right? There's a 10% likelihood I reject, even though I shouldn't be. That's okay. I've set that threshold where I'm okay making the wrong decision 10% of the time. And then if I want to set it so I'm rejecting, if I'm kind of making this type 1 error only 1% of the time, what do? I let alpha be lower, or I set a higher confidence level. I want to be able to say things with 99% confidence. I'm reducing the probability I make a type 1 error. So we have those 3 benchmark alphas, right? I kind of have this set up here kind of already I've talked about this, just we're setting that type 1 error, okay? We won't talk too much into type 2 errors, so I'm going to kind of gloss over this for right now. If we have time, maybe I'll come back to it at the end of class. So we can do this for the difference in means. We could also start to think about, how do I do hypothesis testing for correlation coefficients? It's a different statistic. I could assume that that correlation coefficient is equal to 0. Can I find significant enough evidence that goes against that? That's what we'll end up doing with linear regression, which we should start today and then kind of continue next class. What I want to kind of, and I showed you how to do those t-tests, and we kind of looked at, how we run those in Stata, compare it to the same process. We compare the p-value to alpha, or we could look at the absolute value of the test statistic compared to the absolute value of the critical value. Okay. So a little bit of kind of review where we left off and adding in some new concepts. The next thing I want to think about are confidence intervals, right? So I'll give you this kind of setup, and then maybe I'll draw some stuff out for us. But let's say I want to make a confidence interval, right, that tells me that for every value in this range, I can with 95% confidence say the true mean is somewhere in this range. I don't know exactly where it's at, but with this level of confidence, I can tell you the true value is somewhere in this range. So this could be as simple as, maybe I give you a lower and an upper bound of 10 and 20. With 95% confidence, I'm telling you the true mean is somewhere in between that. Well, how did I come up with that 10 and 20 value? How did I come up with that upper and lower bound? So what we're going to do is say, well, look, we know that we're going to be making these type 1 errors alpha times, the alpha percent of the time, right? Alpha times 100, right? Alpha is always in decimal form. So setting alpha 5, I'm going to be making errors 5% of the time. Okay. Well, I know that the number of standard deviations away I would need to go to get that desired alpha total in my tails. So with confidence intervals, everything's going to line up to the same thing we're doing with two-tailed tests. So if I want 0.05 or a 95% confidence level, 0.025 in each tail, I know that I need to go 1.96 standard deviations to the left and to the right of whatever that true mean value is. Okay. So here I'm thinking about, I want to try to come up with that lower and upper bound, right? Match what I'm saying with what I'm pointing at, such that there's a 95% likelihood that the sample mean I see, if I only have one sample, it's going to be somewhere in this range. Okay. So let's think about what that looks like. Okay. So if I have the true population mean, so let's say I don't have to just assume that I know let's say I actually know what it is. But then I was taking samples from that population data. Well, I know that they should be normally distributed around that true population mean. Okay. So I know that 95% of the time, if I see a sample mean here, and I then build a confidence interval around it, it will include that true population mean. But why? Okay. So I could think about here, if every sample mean that I see, I go 1.96 standard deviations to the left and to the right of it. Well, if I see a sample mean that is anything less than 1.96 standard deviations away, well, then when I add 1.96 standard deviations and subtract my upper and lower bound, if I'm only one standard deviation below, I then add 1.96 standard deviations, this upper bound will be above the true population mean. That's going to be true for any sample mean in this range. Okay. So I'll give you kind of maybe another way of thinking about this that's not in the slides, if I can hit this correctly. So here we go. So if I think about what I'm doing, my sample means will be normally distributed around this true population mean. Okay. If I see anything that's 1.96 standard deviations above and below, so let's say I say a sample mean value right here. How would I create kind of my confidence interval? So what I would do is I'm going to take the sample mean that I see, I'm going to add to get my upper bound, and I'm going to subtract to get my lower bound. Right? So this is kind of like two equations in one. Right? Subtracting will give me the lower bound, adding gives me the upper bound. I'm then going to go 1.96 standard deviations above and below. Okay. Now, let's say I see a sample mean, okay, and that sample mean is, I don't know, 1 standard deviation below the mean. So the value would be, it is 1 standard deviation below the mean, right? If I then add to get my upper bound 1.96 standard deviations, well, a little bit of math shows me that that would be the mean plus 0.96, which means that my upper bound would be somewhere over here. My lower bound will be somewhere down here. This confidence interval, by adding and subtracting that z value that gave me the desired alpha outside of my confidence interval, or alpha in the tails, is going to produce an upper bound such that my confidence interval includes the true population mean. Think about it differently. What if I had a sample mean way out here? Let's say the sample mean value of this was that I was 3 standard deviations above the mean. Well, when I now create an upper and a lower bound around this, we don't really have to worry about the upper bound, but will my lower bound go low enough to include that true population mean? Well, if the value of my sample mean is 3 standard deviations above, when I add to it that z value that gives me the desired alpha on either side of the confidence interval, negative sign, right? I'm getting my lower bound now. So if I subtract here, what am I left with? I'm left with the mean plus, I don't know, 1.04. So my lower bound is still going to be above that true population mean. So anytime I see something that's more than 1.96 standard deviations away, my confidence interval would not include the true population mean. So when I create these confidence intervals, I don't know what the true population mean is. But if I build them around my sample, I can guarantee that alpha percent of the time, right, I'm going to end up with a confidence interval that doesn't include, or said differently, 1 minus alpha 100% of the time. That percent, I can say with confidence, I'll have a confidence interval that includes the true population mean. So we're going to end up making basically the same decisions using our confidence intervals as we would with doing a two-tailed hypothesis test.
We just
Yes?
Yeah.
So if I have a value and it's 3 standard deviations to the right of the mean, to get my lower bound, if I subtract 1.96, have I gotten back to that true population mean yet? No. So my confidence interval is not going to include,
just be short.
Yeah. So it wouldn't include it. So if that true population mean is not my confidence interval, I'm only saying with 95% confidence, the true mean is somewhere in this value, or sorry, somewhere in this range of values. Okay. Is that? Yeah, if I find a sample mean that's not more than 1.96 standard deviations, then when I create the confidence interval, it would include that true population mean. Excuse me. So we can calculate, this is what I kind of have here, right? For any sample mean I see here, when I create the confidence interval, it would include that true population mean. How many times will my confidence interval not include it? So if what I assume to be true is in fact true, I'm going to be making essentially type 1 errors with my confidence intervals. 5% of the time on each side, or a total of 10% of the time, I'll see a sample mean over here, and its confidence interval wouldn't quite include that true population mean. So I am going to be making still type 1 errors if I use confidence intervals or hypothesis testing. So another way of maybe thinking about this, right, is it's basically going to line up with our hypothesis testing. And we'll kind of see this, kind of produce some things in Stata here in a second. And I think we can kind of match these results up and see that it doesn't matter if we do hypothesis testing or confidence intervals, we'll make the same decision. Okay. So I'm going to go through this now and try to give you a little bit more idea of what this looks like, but using Stata. So still going to review a little bit since we're still getting used to Stata. Here's the actual program. I can only open and save data here. You look for what we're going to do in this class, you don't ever need to save the data set. We're just opening up data sets here. So I'm going to go to File, Open. And I think that when I looked at this do file, right, the do file that I had open, so if I try to go to File, Open here, it will show me do files. And if I click on that, it'll open it up in the do file editor for me. But really the only thing I can actually open up here, I mean, I can open up the do file, but the thing that I really want to open up is, if this goes away, whatever data set I want to use. I think we'll go back to the do file to make sure I'm right about it. I think I'm going to use COVID county data here, which I already uploaded to Canvas as a .dta or a stata data file. I said from here on out, I'm not going to worry about importing Excel, importing CSVs. I'll just give you the data file. So here we'll go to this do file editor. We're no longer looking at the regression in class. I uploaded a different do file, which was this confidence interval example, which we can find under kind of this week's stata files. Okay, so that's the do file that I'm going to be using. The data I'm going to be opening up is this COVID data. So here I've got different globals because I open up things on this computer and my laptop. So I have a problem you hopefully don't have, right? You're always opening up files from your specific device. Hopefully they're always on your OneDrive, and you can kind of just set that to whatever your folder name is. Okay. So I believe, let's see, we'll make sure I have the global path correct here today. If not, I can show you a way to kind of remind yourself of what it is. Okay. So it looks like I set it correct, right? So my files I still have back in that week 1 and 2. Once again, you don't have to create subfolders. You can just throw everything into an ECON 371 folder. That way you don't have to worry that your file path is changing if you have different subfolders. So I don't want that because that's not my file path, right? So I've opened up this COVID county data. I'm going to summarize this. So if this is the true population data, I now can see, and this is where in your problem set, you can use that sum command, but if I ask you for the mean, I need to know that you know how to identify from stata's output what the mean is. So you would have to have that sum command, and then in your do file, I said an easy way to do this is use the double backslash for comments. I can identify the mean, and I can identify the standard deviation. So I've answered the question. If the question was, what's the mean, what's the standard deviation? This is the population data, okay? I am not going to expect you to do something like what I'm about to do. This is more complicated in this class, but it's worthwhile going through it to show you what we're saying theoretically can be proven with data. So I told you that the true population mean should be where the sample means are centered around. If I then build confidence intervals around that sample mean, 95% of the time, if I've set alpha to be 0.05, 95% of the time, my confidence interval should include that true population mean. 5% of the time, it won't. So I'm going to create this program, and what it's going to do is it's going to open up that population data. It's going to randomly sample 50 of the observations. So I'm now not working with the population data, even though I know what the population variance and what the population mean is. I now am only going to be able to calculate a sample mean from this data set. Once I have that sample mean, right, I'm going to kind of call this median household income and find the mean. So this will be like the sample of 50 observations. I calculate the sample mean household income. Put that value in a different data set. What I'm then going to do is take that sample mean. Now I'm going to go build my lower and my upper bound. So here I'm going to set alpha to be 0.1, which means I have 5% on either side of my distribution for a total of 10%, right? Alpha of 0.1 is the 10% significance or 90% confidence level. So that's what I'm working with. So how do I do that? Well, the value that would give me 10% total in my tails, or 5% each, is 1 point. And here's where I'd only ever ask you for like second decimals. I went out to the third here, just to be a little more precise. So negative and positive 1.65. I then need to go how many standard deviations away. So this is where we want to be careful. I was writing this as though I'm going to go 1.96 standard deviations to the left and the right. But when I'm working with a sample mean, what do I want? I want the standard deviation of my sample means. So we said, what is the standard deviation of my sample means? Well, if I know the true population variance, it's the square root of that population variance over my sample size. Now in practice, it looks very similar, just changes in notation. I can only calculate that using the sample variance because I don't have the population data. I'm doing a kind of a cool thing here where I've got the population data, so I can show you that if we did just have a sample, that this would kind of hold true, right? So really what I have here for the standard deviation of my sample means is the square root of my population variance over my sample size. Or in practice, if I didn't have the population data, I would just be using the sample variance here. Okay. So once I do that, I can construct, because I could get that population variance back when I had before I started doing these samples. That's what we had. Oh, where is it at? Oh, come on. That's what we had way up here, right? When I just had the original population data. So I'm going to use the standard deviation. It's just a slightly different way of doing this. So if you think about, if I'm taking the square root of the variance, we said that was always going to be the standard deviation. So I just kind of have this typed out in a slightly different way mathematically, but it's the exact same thing. So I'm going to create that lower and upper bound, and then I'm going to create a variable here. Now, when we create a dummy variable, a 1, 0 variable, this is something that you might have needed to do for some of the questions in the problem set. And we're going to do this kind of moving forward. Once we get to regression, we'll talk again about dummy variables. Dummy variable just means the only values I can see are a 1 or a 0. Right? So what I'm saying here is create this dummy variable, and I'm going to call it includes the population mean. It's going to be equal to 1 if the following statement in parentheses are both true, right? So if that lower bound is what? What do I have? Less than the population mean. And if my upper bound is above, right, that means that my confidence interval is including that true population mean. So this variable is going to be a 1 every time I have a sample mean, right, that results in a lower and upper bound that includes this true population mean, which remember, we only knew that because we had originally the population data. Okay. So I'm going to go through and do that. Oh, there it is. I'm then going to kind of summarize this, right? So I'm going to do this 1,000 different times, right? I'm going to take 1,000 different samples, create 1,000 different confidence intervals. Because my assumption I know is true because I had the population data. The true mean is 55,713. 95% of the time, my confidence intervals should include the true mean. Not 95. What did I say I set this as? I'm mixing my examples up. I said I set this to be an alpha of 0.1. So 90% of the time, I'm going to have a confidence interval that includes that true mean. 10% of my values should, or 10% of my sample means will have a confidence interval that doesn't include the true population mean. So I'm going to, yeah.
So you have here a square root 50. So should we already have a number of,
So all I'm doing there,
yeah,
if this is what I'm using.
that's what I'm saying. Like, so like, say it doesn't do that for us. We can put the number up.
So once again, I'm not going to make you reproduce this. If you were wanting to, all I'm doing there is using the value for the standard deviation of my sample means. What's another way I could write this? Taking the square root of something squared is just itself. So that's the format that I use. But it's really mathematically, I'm saying the same. So if I do this, just to kind of prove the point that I want to focus a little bit more on. So if I go up here, I run this program where I take 1,000 different sample means of size 50. Scroll all the way down here. I want to stop here, all right? So I'm going to take 1,000 different sample means of size 50. I'm then going to create the upper and lower bounds. And hopefully once I include, or I create this variable where whether it includes the population mean, when I summarize this, 95% of my observations should be a 1, all right? Sorry, did I say 90 or 95? I set it at 90. So 90% of my observations should be a 1, 10% should be a 0. So hopefully when I run this, we're waiting. Sure enough, 90% of the time, when I created those confidence intervals for 90% of my samples, the confidence interval included the true population mean. 10% of the time it didn't. Now, these are a little bit off. Why are these a little bit off? In order for me to have exactly 90-10 split, I wouldn't need 1,000 samples. I would need an infinite number of samples. We can't, we can kind of prove this to ourselves with data, but we can't really go to the full extent, which is why This class, I don't focus as much on the mathematical proof side of things. We focus more on supporting those theories with data, but you could work the mathematical proof. You would have that exact 90-10 split. We just can't take an infinite number of samples. So I just choose a high number, right? So what if I were to do the same thing? I run kind of the same exact code, but instead I look at, where did I have it here? I take samples of size 1,000. So if I take samples of size 1,000, what should be the case is those sample means are still normally distributed. And when I build my confidence intervals, it should be that 10% of them are so not going to include that population mean, 90% will. So I'll go up here. I'm going to run this second program. Does the exact same thing, but I'm now looking at samples of size 1,000. Okay. So if I run this, what do I end up seeing? Well, here it changed a little bit. If I go back to my code, right, why would this maybe change a little bit here, right? Because if I have larger samples, right, what should be true is that that distribution is going to be a little bit tighter, right? So it's going to be more likely I can reject the null, okay? Now, if I were to continue to like run this program a bunch, I get completely different numbers because it's always generating different random samples. So sometimes it'll be a little bit off, right? A little bit above or a little bit below, but it's going to keep on creating kind of the same, values that are right around whatever that confidence level I set was. Okay. And then I think here, what did I do? Oh, just to prove this to ourselves, what if I wanted the 99% confidence level? Well, then when I construct these lower and upper bounds, I need to go not 1.645 standard deviations away. I need to go 2.58 to the second decimal, or I went to the third here. And so I could do the same thing back to my kind of looking now at sample sizes of 100. If I run this code, what I should end up with, we're waiting. When I set alpha, whoops, I'll make it easier to see. Looks like I forgot to include this, or I accidentally deleted it as I was highlighting things. When I set alpha to be 0.01, or I want the 99% confidence interval, when I take these random samples, 99% of their confidence intervals will include the true population mean, 1% wouldn't. Now, once again, these values are a little off because I don't have an infinite number of samples. So I won't expect you to ever create these programs and run these different, 1,000 different random samples, but I'm using it to prove kind of what we said theoretically is supported by the data. Now, any one sample we have, we're only going to have one sample mean. So I can really only create one confidence interval. And what I'm saying is, based off the fact that I only have one sample, the likelihood that my confidence interval includes the true population mean will be whatever alpha, 1 minus alpha times 100%. So if I chose an alpha of 0.1, what I'm saying is when I create this confidence interval, there's a 90% chance it includes the true population mean. If I set alpha to be 0.05, there's a 95% chance my confidence interval includes that true population mean. Excuse me. Okay, so that's something kind of pushing you a little bit further. Nothing I would expect in terms of Stata for you to do, but just kind of using it to show you the power of Stata A, but also to kind of support this theory that we have with some actual data to prove it. Any questions on that before we keep moving? Okay. I think at this point, we got 40 minutes left. Had some notes for myself over what I want to kind of focus on. Just to kind of prove this point, if we go back and look at that in-class quiz, you don't have to open it up. I'm not going to have you respond to it. I just want to review one of the questions that I gave the answer to. So we're looking at question 1. Okay? If I wanted to build that 99% confidence level. Okay? Well, this is where I'll show you kind of some nice tricks, right? So I have a sample of 50 individuals. I find a sample mean of 102, and I have a known population variance of 144. Okay? So if I want to build the upper and lower bound, what am I going to do? Okay? So the general form is that we're going to take our sample mean, we're going to add to get our upper bound, subtract to get our lower bound. Now, we need to go a certain number of standard deviations away. That gives us half of alpha in each tail. So before I was giving you these values, I'm going to show you how using the t-tables you can always find this. Okay? We're going to multiply this by the standard deviation of our sample means, which we said we could rewrite this then as, well, what's the standard deviation of our sample means? It's just the square root of that population variance over our sample size. We know this is 50. I think I told you this was 144, and I think I told you the sample mean was 102. So the only thing left we need is how many standard deviations do I need to go above and below this sample mean to create that confidence interval. So what I'm going to do here is pull open. I gave them to you a while ago. My OneDrive will respond here in the next. We're waiting. Okay. Maybe I broke the computer here. We'll see if it responds here. Well, maybe we can do this quicker. I don't really want to switch off this because it'll take time. Here we go. So I gave you those kind of Z and T tables. Really, for all what we're going to do in this class, we actually just can rely on this T table. Okay? I'm not going to make you look up the T values. In this case, I gave you a known population variance, so you know that you really should just be using that standard norm. Even if you have a sample variance, we said as the sample size goes up, our student T distributions get closer and closer to a standard normal. So for the sake of everything we're going to do in this class, when you want to find that number of standard deviations that gives you the desired alpha over 2 on your tail, when we had an alpha of, now I already forget, what was it? 99% confidence. So what would my alpha be here? So if there's 99% within my interval, there is 1% outside. Alpha is always the decimal form, so my alpha would be 0.01. If I've got two sides of that confidence interval, or a two-tailed test, how much is in each side? 0.005. So when I go to that T table, I want the value that gives me 0.005 in one tail. The table tells me the area in one tail. I can go all the way down, and this last row basically tells me what the standard normal values would be. For anything I ask you to do, I'm not going to have you use degrees of freedom and identify it. You can always just use that standard normal value to approximate. So for us, that value is going to be 2.576, right? We now have the last piece of information that we need. Right? This is just now just a simple equation, right? I'll add here, and what we call this, we might start using this term. This is our margin of error, right? It includes multiple things, but if I just want to refer to it with one name, this is my margin of error. I'm going to add it to get my, all right? So if I add it, I'm getting my upper bound. When I subtract my margin of error, I'm getting my lower bound. Okay? So what's going to happen? Let's say I maybe asked you a question like this. Maybe on the quiz, I gave you 3 confidence intervals and asked you to arrange them in order of the 90, 95, 99%. What has to be true about the lower and upper bound of the 99% level relative? So if I'm basing this off of the same sample mean, if I compare that to the 95% confidence interval, what has to be true about my upper and lower bound? Well, if I want the 95%, the area in my tail is going to be larger. So I'm going to go how many standard deviations away? Fewer, right? If I go fewer standard deviations away, I'm adding and subtracting a smaller value. I know that for lower levels of confidence, my confidence interval is going to be narrower, right? Or in this case, my lower bound would be higher and my upper bound would be lower. And if I want to do the same thing, but I wanted a 90% confidence level, if I'm basing it around that same sample mean, my confidence interval is going to be even smaller. When I want to say things, right, with lower, when I want to say things with kind of higher levels of confidence, what do I need to do? Expand the values that I'm making potentially the population, right? I need to, if I can say with 90% confidence it's in between 5 and 10, in order to say with 99, I have to tell you it's somewhere in between something larger than 5 and 10, right? My upper and lower bound have to be even larger in absolute value. So this is kind of just the concept of confidence intervals. The higher the amount of confidence we want to say something with, the wider those intervals will be. Okay. Any questions on this idea? I probably spent a little more time than I needed to, but it'll make some of what we talk about with linear regression go a little bit quicker, I think. Okay. Questions on that? And so I don't know, I can't do that math in my head. But if we plug this into our calculator or plug this into Excel, that's what should have then reproduced these values that I kind of just gave to you when we looked at this in class quiz before. Yeah. So just also to kind of prove something, what should my lower bound always be? Below my sample mean? And what should my upper bound always be? Above my sample. And this is just one way to make sure I'm not making egregious math errors, right? Remembering these concepts, especially if I give you like multiple choice, or it kind of helps me rule out some obvious answers when I remember the concept of what I'm doing. Don't get too lost in the weeds or the equations. Remember these general concepts, and a lot of time you can rule out very obvious incorrect answers. All right, any questions on that before we keep moving? Okay, so here's where I'll probably update these slides after class because I don't know how far we're going to get. Wherever we leave off, we'll pick up next week, right, on module 4, or week 4. So I'm going to go through the first part of this very quickly. Should be somewhat review. You probably talked about regression like at the end of 370 is my guess, or you should have. So what we're trying to do, as I said, we can do hypothesis testing or confidence interval construction for any statistic. It doesn't just have to be the sample mean, it can be the difference in sample means, could be for the correlation coefficient. Well, what we're actually going to do is try to come up with a better measure of correlation than the correlation coefficient. So what we're going to do is we have two variables. I have an x variable and a y variable. And I want to know, as x goes up, does y tend to go up or down? That's kind of what the correlation coefficient told us. But we're going to see that when we use regression, we can make even more powerful statements. Okay? So if I'm thinking about this, what am I really doing? I want to know if I had an equation that represented the relationship between x and y, what is the slope? Is it positive or is it negative? And how large of a positive or negative value is it? What does this look similar to that? Hopefully you're using other econ courses. If y was price and x was quantity, you're back to econ 101 or 250, I guess here it's 251. But right, you're back to introductory, right? I've just got a demand equation. I can use prices and quantities to estimate what that relationship is. Hopefully, if what we've told you is correct, what should the value of beta 1 be here? Or what should that slope be? If I want to see people buy more units, the price is going to go down, right? Or vice versa. I should see a negative slope here. So these, you might not be as common, you know, I already mentioned, I called them beta, right? It's just the terminology that we use with regression. Beta 1 is my slope. Beta 0 is my intercept value, right? My intercept is the predicted value of y when this x variable is equal to. When would y just be equal to beta 0? When x is 0, right? Because then no matter my slope, anything times 0 drops out. So we can estimate using data what the intercept is and what the kind of slope is between two variables, right? So some terms that we'll start using, I'll call y my dependent variable, right? It is what depends on the x variable, right? Now, as we get later on, this will make a little more sense because we're going to have y as a function not of only one x variable, but multiple x variables. For now, we're keeping it simple. This is simple linear regression before we move to multiple linear regression. Okay. My independent variable is the thing that's changing. X is changing, and as a result, when I use that equation to calculate y, y is what depends on x. So as x changes, y is then going to respond, right? Or y would change in kind of response to that. Okay. So if I'm looking at the scatter plot of the data, which we've already looked at how we do that in Stata, we said what gives me an idea about the relationship between two variables is if I were to look at this scatter plot and try to think of a line that best fit that data. So if I have a line that best fits this data, that's my simple linear regression. if I have this line, I now can come up with the intercept, and I can also come up with the slope, right? So what we're ultimately trying to do is use data, use all these data points to estimate the relationship between X and Y, and to come up with an equation that tells us what that relationship is, right? So I could think about, if I had a scatter plot that looked like this, what is my slope probably going to be pretty close to? If I had to draw a line that best fit this data, it's pretty horizontal, so my slope would be not 1. As X changes and Y basically stays the same, our slope is actually 0, right? There's no relationship. X can change and Y doesn't respond. Now, what if I had something that looked like this? Well, here, as X goes up, Y tends to be higher. I have a positive relationship, or beta 1, my slope would be positive. Now here, I've got a linear relationship, right? There's no difference with these X values. The slope is always the same. I could have the same thing, but a negative relationship. We are not going to get there for a while, right? For right now, we're going to assume linear relationships. Eventually in this class, we will talk about how I can estimate nonlinear relationships. My guess is in 370, you didn't talk about this at all, right? So this is eventually kind of not going to be reviewed when we get to this point, okay? So here we're going to think about, all right, I have these two variables. How am I going to use this data to come up with this line of best fit? Because I can't just eyeball the scatter plot, right? That's not a very technical way of doing this. So what we want to do, and here I think I accidentally hit that. Maybe it changed on my screen, but not on the projector, right? So what we're going to do is say, look, if I had this line of best fit, it's going to help me come up with predicted Y values for every X value, okay? So I'm going to draw this out for us. I think maybe I can build this to help make a little bit more sense. So let's say I have my X variable, I have my Y variable, right? Here's the actual data points. Looks like here I have a positive relationship. If I were to draw a line that best fit this data, what that's really telling me is it's giving me Y as a function of X. But this is kind of like, what would the average Y value be, or the expected Y value be for this specific X value? All right, so we can think of really our line of best fit is only giving us predictions for that Y value. You know, for any persons, for example, anyone with a college degree, if I want to know the relationship between that and their income, well, I can make a prediction on average what your income is with a college degree. But for any one person, I'm going to be way off if I try to estimate that for, I don't know, Bill Gates, right? My prediction is going to be way off of his actual income. So for any one observation, we might have our predicted Y value for that given X, but this person's actual Y value is right here. So we're going to say that difference between our kind of predicted, our actual and our predicted Y values, this is going to be what we call epsilon, or our error term, okay? So here, right, the error that exists, right, is going to be some positive amount. My prediction was too low. Now, what if I think about an X value down here? For this particular observation, I kind of crossed out that point, right? Well, now my predicted Y value for that observation is above the actual Y. So here, my error term, my prediction is actually going to be a little bit too high. The actual Y value is higher. So we're going to be making errors in both directions if we just use this line of best fit. You can think of this line of best fit as telling me the average effect of an increase in X, right? But for any one individual or any one observation, I'm going to be a little bit off. So what we're going to try to do, theoretically, right? And I think if you look at the book that I think I had to assign a textbook of this course, even though we're not going to use it. But if you were to look at it or look at online resources, sometimes this error term is referred to as U. It's just a different notation. But I always write epsilon because it looks like an E. and it is the error term. And you'll see other textbooks use that. I think it's a little more intuitive. Okay. So what am I going to do? For all of these predictions, we said we're going to have some observations where I'm making positive and negative errors. When I'm making a prediction, do I really care what direction I'm off by? No, I just care that I'm wrong, right? So what we want to do is we're trying to choose a line such that the errors that we're making across all the observations are as, do I want to make big errors or small errors? Small. So I want to minimize all the errors I'm making. This is a little bit more complicated, so what am I doing? I'm trying to minimize the sum of all the errors I make for every single observation. Now, similar to the variance, if I don't care what direction I'm off by, when I square that error, positive or negative errors end up being the same value. Negative times a negative is positive, positive times a positive. I don't care what direction I'm making the errors. Now, when I square it, what do I also do similar to the variance? When I make larger errors, when I square that, it's going to overpenalize that, right? 1 squared is 1, that would get added in, but 2 squared is 4, right? So just like the variance, by squaring it, we not only kind of get the absolute value, that's just the fact that we made an error, but we overpenalize really bad errors, okay? And then you could kind of write this out. What was the error term? The difference between y and the predicted y. If you then want to say, how am I coming up with a predicted y? Based off my line of best fit. Well, what was my line of best fit? Y was equal to beta 0 plus beta 1 times x, just that simple linear equation. If I then think about how do I minimize an equation, choosing 2 values, not everybody has the same math background here, but I would take a derivative in respect to both of those. I now have 2 equations, 2 unknowns. I could then solve for what those values are. I'm not going to make you go through this, but this is what state is going to do behind the scenes. And in fact, it's even more complicated, right? Because yes, I'm taking a derivative, but each one of these is not one single value. This is every single observation's y value. So this mathematics is a little bit more complicated, but the general concept, hopefully in some of your math courses, or even in, I think, like game theory and stuff, you're going to have to do something similar to this, where if I have 2 unknowns and I want to choose them such that I'm maximizing or minimizing these out, I would take a derivative, set the equations equal to 0, 2 unknowns, 2 equations, I can now solve. That's all the state is doing behind the scenes, okay? So really what we're doing with linear regression is we're trying to come up with a line of best fit that minimizes the sum of all the errors we're making squared, okay? Any questions before we kind of push it then to looking at the actual results that state is going to give us from these regressions? So this is a little bit of the technical side of things, but another interesting thing that comes out of this before we get to the actual data is when we try to, from a simple linear regression, when we try to get this predicted value for the slope, so the slope of that line of best fit, what it ends up being, if we like went through all the math and actually did the derivatives and, you know, solved for beta 1, it ends up being the covariance divided by the variance of x. So it's going to be that covariance, right? Or we already talked about this. What is the covariance? So this is where it's kind of, I'm cheating a little bit. I kind of skipped a step in the slides. So if I'm thinking about the covariance between 2 variables, we said that was the sum of the deviation of x from its mean times the deviation of y from its mean divided by our sample size. If I then wanted I told you that that beta 1 predicted value was equal to the covariance divided by the, standard deviation of x. Well, that would be what? The square root of the variance, which was the deviation of x from its mean squared over n, right? So you can kind of see here, like I've got, and sorry, I was looking at, thinking about here, I've got kind of n in both situations. I've got deviation squared here. You can imagine if I did some simplification, this kind of drops away. I'm taking the square of a square root. This is not exactly how it's working, but just kind of give you an idea of where this is coming from. I'm really just taking my covariance, dividing it by the standard deviation. Or sorry, not standard deviation. That's why the math works out better. sorry, I don't take the square root here. I'm looking at the variance, right? I wrote that without even looking at what I'm doing, right? So if I have n and n, this cancels. I can kind of see how that would cancel. I've got something squared divided by itself. But basically, if we simplify that equation, we'll end up with, it's just the covariance over kind of our variance, right? So we can prove this to ourselves with data because we already talked about in this data how we calculate the covariance, right? Or we can at least, I'll show you how we can look at covariance matrices. I can also look at the variance. We talked about how I can calculate the variance standard deviation of a variable. So we'll eventually prove this to ourselves. Probably not today, but definitely next week. Okay. So another nice thing that will kind of come out of this is once I have that predicted value for the slope, the predicted value for my intercept will simply be the average y value minus that predicted slope times the average x value. Okay. So if I can calculate means from my data set and I tell you either the intercept or the slope, you can always solve for the other one. Okay. All right. So if I look at this, I think I kind of already mentioned, but this is the covariance. My denominator is the variance. We can find these statistics already. So we can actually find these slope values without actually running a regression in Stata. We'll kind of show no matter if we do it either way, we'll come up with the same value. Okay. So I left this slide open so we can start to think about how do I do this in Stata? Okay. This is primarily what we're going to be doing for the vast majority of the rest of the semester. Okay. So I have that do file on Canvas. It's called regression in class S spring 26. Right? I'm going to have to set my global file path. So once again, I have multiple ones here, but that's only because I'm using multiple computers. You would change this to I:// whatever your folder name is. You would then kind of download this data. What is it? Birth and fracking data, which once again, from here on out, I'm only ever going to be giving you .dta files. So you should be able to open these up pretty easily. But the code that we're going to use to do that will always be use just wherever your file path is and the name of the data set. So I've got my global path set. I'm going to open up that data. I'm then going to look at this scatter plot, which we've already done before. So if I look at this, well, might have accidentally clicked on the wrong one. There we go. So this should open it up. Okay. So that means I probably forgot where I put this file. So let's see where I had it. I want birth and fracking data. So I open this up. Don't save. So what did I have? So this is kind of a cheat way. If I open something from the interface, if I forget where my file path is, I can always kind of copy and paste that. So I make sure that I didn't make any like egregious like spelling errors or something. So now if I set this global path, hopefully I probably move some subfolders around here. Now I'm able to actually open up that data set. So I just had an error somewhere because I was probably moving things around. When I originally had this do file, probably put things in subfolders. So if you're ever kind of like, why is my file path not right? You can always go to file open. It then tells you the code of exactly where it's opening from. And you can always then just copy and paste your file path to make sure if you're creating subfolders that you're choosing the right one. Okay. So if I looked at this, opened up this data set, I then look at my scatter plot. Whoops. I got rid of my scatter plot accident. Well, this is kind of hard. Like if I'm drawing a line of best fit here, I've got some really weird data where if I'm looking at the total number of shale wells, so this is like, I think it's kind of out of like the public discourse now, but fracking was a thing that people were talking about a lot. So it's like a way to like produce oil and how it was really bad for the environment and potentially was actually causing like issues with people and causing birth defects, but also like what word am I looking for? Like stillbirths, things like that, right? So maybe when I have more of these shale oil wells, I was actually seeing birth rates going down, right? Because it was having negative impacts on people who were pregnant. Now, it's hard for me to see if there's a positive relationship here. The data is kind of weird. So it's hard to rely on our eyes. It's kind of hard to eyeball what that line of best fit is. In fact, we don't just want to eyeball it. We want to actually minimize the sum of the squared errors to determine what that actual line of best fit or what the actual relationship is between the number of fracking wells and the number of births. Right? So I have in this data set, how can I do that? all I have to do is use this reg command, stands for regression. If I run this reg command, the first variable I put is my y or my dependent variable. So for me, that was, I'm trying to predict the number of births, and I think this was like county level data. How am I trying to predict that? I want to know the relationship between the number of births and the number of these wells, right? So the independent variable, the thing that's changing that I think might be impacting births is the total number of shale wells in that county. So this is basically running our regression. It'll be able to come up with the predicted Y values based off of these X values. Look at the errors I'm then making between the actual Y values and the predicted Y values. Look at all of those errors and choose beta 0, the intercept, and beta 1, the slope, that minimizes the sum of those errors squared. It's doing a lot of work for us, right? It's doing a lot of work behind the scenes for what? A data set that has 170 observations, right? It's going to take me a lot of time if I try to do that by hand, right? So I'm going to run this regression, right? And what it tells me is the following, right? These coefficients, those are your beta 0s and your beta 1s. Beta 0 is your intercept, right? That y-intercept, or what the kind of Stata calls the constant, right? When I'm making predictions, it's the thing that always gets added in. It's the intercept, it's the constant in that equation. So beta 0 will be 6,145. So how can I interpret the intercept? We said, if I'm thinking about an equation, and I have the number of births as a function of the number of these kind of wells, or these shale wells, right? Beta 0 will be the predicted value of the number of births when I have 0 wells. That's how we interpret the intercept or the constant. It's going to be different if we have different variables, in the sense that, like, I'll, instead of saying when there's 0 wells, if I was trying to predict somebody's income based off of, I don't know, something weird like their height, it would be their predicted income when their height is 0. So we get some weird interpretations with the intercept, because a lot of the times we have variables that we can't actually see 0, right? Or I could think about, what's the predicted income for someone with 0 years of education? Well, it's likely we're not going to see that in the data, but that's still where our line of best fit is going to start. So you could think about, if I try to do something like my X variable or my independent variable is education, and I think about income, well, most people, I mean, even if you dropped out like compulsory education laws, you're probably still going to high school, right? So most of our years of education, our scatter plot is going to like start up here. And then as you get more education, hopefully it's increasing your income. But that line of best fit, you're still going to have an intercept for the point of 0 years of education. So that's always how we interpret the intercept, even if that interpretation is a little bit odd. Right? So for our example, it was the predicted number of births when there are 0 wells in that county. Okay? So in fact, not only is that the interpretation, we can give the exact value. When there's 0 wells, the predicted number of births on average across all counties here was 6,145. Now, what is the interpretation of our slope coefficient, or beta 1? Well, that coefficient column tells us what the value is associated with this variable. The variable X we had was the total number of wells. So if I had a general equation, what does the slope tell me? How much Y increases when X goes up by 1. Our regression is the exact same thing. When X goes up by 1, our slope, beta 1, is the predicted increase in Y. So here's where we have to think about, use economics. We're not just purely doing math. We need to know, what is the unit of our variable? Well, here it's the number of wells. So if I have 1 more shale well in my county, the predicted number of births is going to go down by 3.9. Okay?
Like, for example, you use scatter plot and show it like that. So that particular one, the scatter plot is based on
That's going down. If my slope is negative,
so what that thing, technically, like the scatter plot that you showed, majority of the points just came off it, and then continue.
so this is a good point, right? When I look at this, I might think that there's a positive relationship. Sometimes it's hard to eyeball. If I use the actual, if I try to minimize the sum of my squared errors, the actual line of best fit here is downward sloping. I know I have a lot of points here at 0, but it's still using those values when it's choosing beta 0 and beta 1 to minimize the sum of my squared errors. So this is a good example where the scatter plot, I might have thought this line of best fit was something completely opposite of what it was. And it's because we're not, when we view data, we don't really, it's difficult for most of us to like conceptualize what it's actually showing us when we have some like not obvious examples. Some of the obvious examples, it's easy to see what my line of best fit is. Here, because I have a bunch of points with an x value of 0, it's harder for us to think about what this line of best fit actually is.
And if you discard then, so that you already found a prediction point, how you
What do you mean? So you don't need points at every x value. So think about it this way. If I was trying to come up with a relationship between height and weight, how can I actually measure height? Out to whatever decimal I want. Am I going to have someone who is exactly 63.15629578431 inches tall? No. I'm always going to have gaps in my data, right? I'm using, in fact, if I only have 30 observations, I'm going to have a ton of gaps in the data. I'm just using the data I have to say, well, look, this is the power of a regression. I don't even have to have observations that have this x value, and I can predict what that y value would be if I did see that in my data set. So I could think about, even though my data set might be limited to 50 observations, I'm not going to be able to see every single person's income value. But I can make predictions for any income value that's in that range. Is that what you're asking? Yeah. I don't need data at every single x value. I just need a sample to come up with this line, and then from that line of best fit, I can make predictions for any value, even if they don't show in my data set. Okay? Is that what you were asking? Okay. Okay. So maybe to your point, another thing we might want to do, and this is where we start to have to use what we're talking about in terms of data with like our economic intuition and knowledge. So what was weird about that data? There was a lot of counties with 0 wells. They might be kind of skewing my results, right? So I said, okay, what is this relationship between births and the number of wells? But just like we can use conditional statements to calculate means, I can run a regression only for observations that meet a certain condition. So here, I'm going to run a regression where it only uses the observations where the number of the number of wells was not equal to 0. So what this is really telling me is, assuming that they have at least 1 well, does then adding more, right, actually increase or decrease births? In other classes, you might have talked about this, extensive and intensive margins, right? Just having 1 well, just having some operations of fracking might cause a really large impact on births. But then what happens as you have more of something? Generally, just like when you consume it, the marginal benefit is declining. So maybe the marginal effect of having these wells, maybe initially having 1 is huge, then each additional well doesn't really change much, right? So maybe I'll get a different result here. In fact, if I run this regression and I just say I'm only going to want to use the observations where I have some positive number of wells, because we can't have negative wells. And once again, reiterating, if I want not equal to, we said in Stata, this is a exclamation point equal sign. Okay. So I'm going to kind of run this line of code. Now what do I see? Okay. Now the effect of having an additional well looks like it's not quite as strong. Here, instead of reducing the number of births by like 3.9, it's only reducing it by about 2.2. Okay. So maybe looking at kind of this different data set, what does this tell me? Well, the kind of intensive margin here might be larger than the extensive margin. Or, in other examples, maybe it's vice versa. I wouldn't kind of push you as far as to like say that, but just kind of using this as an example to show if I'm looking at a specific relationship, I might want to look at it only for a specific subset of individuals, right? I would think about this as like if I'm trying to predict the returns to education, an additional year of education probably has a much different effect if I'm going from only having 9th grade to 10th grade education. If I go from having 1 to 2 years of college, those returns might look very different. Same increase in 1 year, but they might look very different for an additional year of college education versus high school. So I can use these conditional statements and run regressions there as well. Okay. I then did a scatter plot using kind of that same condition. Here, once again, it's kind of hard to see this line of best fit, which is why we want to rely on Stata to do this minimization of the sum of the squared errors for us. It's really hard with some of these scatter plots to kind of just eyeball the data. Okay. So, got 4 minutes left here. I think what I'm going to want to do is hold off. And since you're here today, I want there to be some value added. So I'll let you on a secret. And I'll probably stop the recording right now.